Welcome back, everyone. I'm Professor Rhett Smith for ProtonGuru.com. Today we're going to be covering Lesson 4.12, and we're going to continue our discussion of substituent effects on electrophilic aromatic substitution processes. In our last lesson, we talked about how a substituent on benzene would affect the rate of the next electrophilic aromatic substitution process. Well, if there's already a substituent on the benzene ring, we actually have three potential isomers we can form when we add a second substituent. Let's consider that we have a substituent X already on the benzene ring here in box A, and the next substituent E, an electrophile, comes in and adds either ortho to that existing substituent, meta to that existing substituent, or para to that existing substituent. Well, is there any preference for one of these isomers, or is one of these disfavored? Well, we'll have to go and figure this out. And in order to understand which product or products are favored in the highest yield, we need to examine the mechanism, which we've already studied for the electrophilic aromatic substitution processes. And we need to keep in mind the general principle we've been talking about throughout all of organic chemistry. And that is that the more stable intermediate leads to the major product in the majority of organic chemical processes. This next slide looks very, very complicated, but what we're really doing is considering that we have an existing substituent Z on the benzene ring. All right, and then we take an electrophile E and we add the electrophile either ortho to that existing substituent, meta to that existing substituent, or para to that existing substituent. This, of course, leads to the carbocation intermediate we've been discussing for all of these electrophilic aromatic substitution processes. Now, when you're trying to think about, okay, we're trying to find the most stable intermediate, the most stable carbocation, and these carbocations we make happen to have additional resonance contributing structures. We must consider all of the resonance contributors in order to figure out which of these cations is the most stable. So for the purpose of doing this, it's important to know what substituent Z is. Let's say that substituent Z for this case is a resonance donor. So I've drawn a lone pair in on that substituent Z here, here, and here. It's important to know that's a resonance donor because, well, as the name suggests, a resonance donor substituent can donate electrons to help stabilize some resonance contributors. So let's see what happens in this particular case. Well, we can draw a resonance contributor where we take one pi bond and move it towards the positive charge here in the intermediate. That will give us the species in box A. That species can undergo additional movement of electrons to show how you would access this resonance contributor, which I've already sort of drawn out on the screen for you. And then because this is a resonance donor, we can have donation of the lone pair from Z down to that carbon, and that gives us 1, 2, 3, 4 resonance contributors. And in these 4 potential resonance contributors, we also see that the substituent Z can help stabilize the positive charge. That occurs when we have the ortho substitution. So that suggests that the ortho substitution pattern has some extra stabilization. Well, that could be true for all of these. We haven't examined them all yet. So let's keep going. So we look at this meta substitution pattern where the E we just added the electrophile is meta to the Z that was already there. Well, we can draw an additional movement of electrons here, and that gets us to this resonance contributor. We can continue to push electrons around the ring, and that would give us the resonance contributor in box B. Well, we can't draw any additional resonance contributors, so we only have 3 contributors here. Well, that's not as many resonance contributors as we had up here. We don't have as good of a resonance delocalization when we have the meta substitution pattern as we did for the ortho. Furthermore, you see that the Z with its lone pair is kind of skipped over. In order for Z to do resonance donation to the carbocation, at some point in one of the resonance contributors, you need to have the plus charge beside the Z. Because of where the plus charge started and how it hops around the ring, alternating and skipping carbons, you see it never gets to be right beside the Z. So there's no special stabilization of that carbocation that is attributable to the substituent Z. How about in the case where we do a para substitution pattern? Well, we have the plus charge here to start with. We can move this pair of electrons over here, moving the plus charge here. That gets us to this structure. And now we have a choice between moving this pair, which will get us to the structure in box C, or we can take the lone pair on the resonance donor Z and donate it to make this double bond here. In that way, just like in the ortho case, we have 4 resonance contributors we can draw, and in one of them, we see that the substituent provides special stabilization of that structure. So the ortho and the para substitution provide the most stable intermediates. Now they both have 4 contributors. They both have that Z substituent poised to help stabilize the carbocation. So there's no difference between them. Our conclusion is that we should get a mixture of ortho and para isomers anytime we start with a resonance donor on the ring. And remember, we're talking about the Z, the resonance donor, already being on the ring before the electrophile adds. And I want to point out that these resonance donors are the same groups that we called activating groups in our previous lesson. So the same groups that are the most activating, that speed up the rate of electrophilic aromatic substitution reactions the most. They also are the best at stabilizing the carbocation intermediate, provided you use electrophilic aromatic substitution to place the second substituent on the ring. Well, what if we have a halogen on the ring? Let's say the X is fluorine, chlorine, bromine, or iodine. What influence will that have on the carbocation? Well, we can take this carbocation and move it around the ring to get, first of all, the resonance contributor shown here in box A. We can further move around the ring, and that places the plus charge here. If we take a look at the case where a halogen's already in the ring and then we add this electrophile, we can see that we have the positive charge here to start with. It's always right beside the added electrophile, right? We can move the positive charge around the ring first here and then move this pi bond, and in that way we'll get the positive charge here. Moving on to the case where the added electrophile is para to the X that was already there before the electrophile added, we can again draw this resonance contributor and this resonance contributor. And what we can see is that in each of these cases, the ortho, meta, and para substitution pathways, we have 3 resonance contributors in each case. And the halogen groups are not resonance donors. So even if the plus charge ends up beside the X, remember the halogens are not good at doing resonance with a positively charged carbon. So what influence do they have? Well, they have an inductive effect. So none of these carbocations are as stable as they would be if the X wasn't there. We talked about that in the case of the rate discussion we had in lesson 4.11. But although each of these is less stable than the case where the X isn't on the ring, the halogen can provide some stabilization if the plus charge is right beside the halogen. And this is quite related to what we saw when we talked about carbocation stability way back in lesson 1.11, when we said, okay, if you have an alkyl substituent beside a carbocation, you have the sigma bond, and that bonding pair of electrons is attracted to, it can't do resonance with, but it's attracted to an empty p orbital. This effect is called hyperconjugation. If you think about the fact that the halogens, whether it's fluorine, chlorine, bromine, or iodine, all have 3 lone pairs, and they can't engage in resonance with the plus charge, but there is a pair to be attracted. You can think of that as being an effect similar to hyperconjugation. Now you can't really call it hyperconjugation because that term is very specific, and the definition of that term is that it is an attractive force between a sigma bonding pair and an empty p orbital. So although this is a pair of electrons, it's not a sigma bonding pair. So it's a hyperconjugation-like attractive force is how we can think about it. So with that in mind, that this non-bonding pair near the positive charge on the carbon helps stabilize it a little bit, we can look back here and say, okay, where do we have that stabilizing influence? We have it here in the ortho case. We don't have it in any of these meta cases, but we see it again here in the para situation. So we expect that the ortho and para carbocation intermediates would be a little bit more stable than the same meta isomer. So coming back to this page, we conclude that the ortho and para products would be the major products in this case as well, if we had a benzene ring that had a halogen on it and tried to do electrophilic aromatic substitution. Well, let's consider if we have an inductive withdrawing group, Z, something with a partial plus charge on it, let's say. Okay, so we have something with a partial plus charge, and we look at placing an electrophile ortho to that, meta to that, or para to that. And we again consider the different resonance contributors. We can fill in this contributor, moving the positive charge here. We have Z with its partial plus charge and the electrophile ortho to it. And we can move this positive charge one more time. Well, you might be able to tell that this is unfavorable to put a positive charge right beside a partial positive charge. That seems kind of bad. How about in the meta case? Well, again, we can draw the movement of the plus charge around the ring. We can move it again to make the third resonance contributor, which would look like this. And here's our Z with its partial plus charge. There's the electrophile. Again, I'm leaving the hydrogens off for now. In the para case, we can again move the pi bond. Oh, the plus charge is going to be beside the Z group there. That seems to be bad. But we can move this pair of electrons again and create, again, a third resonance contributor. So in all these cases, we can have a set of 3 potential resonance contributors to each structure. But in 2 of the cases, para and ortho, you have an actual unfavorable situation where the Z group is beside the positive charge. That's a repulsive force. We would expect that to make the ortho and para carbocations less stable. That means we would anticipate that the meta substitution product would be the major product. So the general trend worth noting is that we can correlate a substituent's electrophilic aromatic substitution reactivity group with its electrophilic aromatic substitution directing ability. Right? We talked about reactivity and the rates of the reaction in the last lesson. Now we're talking about if there's already a substituent, where does it direct the next group to go? First, consider that the substituent can only be beside the positive charge in one of the resonance contributors when we have either the ortho or the para substitution pattern, where the newly added electrophile adds ortho or para to the existing group. Well, if having the substituent next to the positive charge helps to make that positive charge more stable, then ortho and para, a mixture of those, will be the major product. So we really need to know for which of these substituent classes we talked about in our last lesson is the substituent stabilizing for an adjacent carbocation. Well, we have 3 groups that do this. The activating groups are the resonance donors, so they will be able to help stabilize the carbocation if they can be beside the carbocation, which happens when you have the ortho and para substitution. A slightly activating group are the hydrocarbons, like alkyl groups. An alkyl group being beside a positive charge is very stabilizing. We saw that the more substituents you put on, the more stable a carbocation is. Finally, even the slightly deactivating groups will help stabilize the carbocation if they're right beside it. Now, the overall carbocation, for considering all the resonance contributors, is less stable than if that X wasn't there, but there's a little bit of favorability for having that halogen right beside the positive charge compared to it not being right beside it. That leaves us only with a case where the positive charge being adjacent to the substituent would lead to a repulsive force. This occurs for deactivating substituents. Now, if you have a deactivating substituent that would repel the positive charge if it's beside it, you do not want to place that substituent next to the positive charge, which happens in the ortho and para positions. So the major product will be the meta substitution product. So all the substituents except the deactivating lead to the ortho and para products as being the major products. The deactivating substituents are the only ones that lead to a meta substitution product. Well, let's look at a few real-world examples. Here are 3 electrophilic aromatic substitution reactions, and we're asked to provide the major products. Well, first consider which reaction this is. This is a halogenation reaction, and specifically a bromination reaction. So we need to substitute an H for a bromine. Now, where does that bromine go compared to the group that's already there? Will the major product be here, here, here? What is the major product or major product mixture? Well, we have to consider the type of substituent we have here. This substituent has a partial minus partial plus because of this polar bond. Well, a partial plus next to the ring is a deactivating group. All right, and we know that if we have an ortho or para substitution, if X goes here or here, our next group, in one of the resonance contributors will have a positive charge right beside that partial positive. So the ortho and para carbocations are destabilized in such a case. We should get the meta product as the major product. So the product would look like this if we just add the bromine on there. That's your major product. In this next case, we have an oxygen, and we know that oxygen is a good resonance donor, or an activating group. So I'll just abbreviate A for activating group. And the reaction conditions are nitric acid with sulfuric acid. If you remember, that is a nitration reaction that places an NO2 nitro group onto the benzene ring. So considering what's already on the ring to help stabilize the carbocation or destabilize it, we have a resonance donor. We know that that would be favorable when we make an ortho or a para substitution pattern, the carbocation intermediate resulting from those substitutions. So one of our products should be the nitro group ortho to that existing group. So I'll just redraw that existing group and put the NO2 group on there. Now another of the products should be the para product. So we already have this group, 1, 2, 3. We put the nitro group on here. We would expect a mixture of these two products for reaction B. Finally, we have a Friedel-Crafts acylation reaction. The aluminum trichloride would be expected to pull the chlorine off. It's a very strong Lewis acid. And now you'd make this acylium cation. And if we look at the group that's already there, it's a halogen. The halogen is another of these substituents that will favor ortho and para substitution. So if you know how to categorize these substituents and understand whether they will stabilize or destabilize the carbocation resulting from ortho and para substitution, you'll be able to figure out whether you have a meta product as the major product or a mixture of ortho and para. In our next lesson, we'll talk about some more subtle features that can also influence your distribution of the products.